Hi guys. All right, chemistry. Unit 1, pardon me, is going to be an introduction to chemistry itself and also an introduction to some of the math that we will use throughout the year. So it's kind of a long PowerPoint, so bear with me. I'll tell you on some of the pages that we're just doing examples, and you don't necessarily need to write it down, or we'll kind of skip through it kind of quick. So here we go. So chemistry, as you know, is the study of matter, what it's made of, and then any changes that it undergoes. So chemical, physical, nuclear, and we will study one branch in particular, and that is inorganic. Inorganic, of course, means that we're dealing with things that are not living. And so it is kind of the general chemistry a lot of times, like in a college course book. There are also the fields of organic chemistry, which is carbon-based chemistry, which most living organisms are based on, or most, I would say all probably. Analytical chemistry is trying to figure out what something is made of. So you're analyzing the chemistry of something. Physical chemistry is kind of a combination between physics and chemistry, and it has a lot to do with the energy field. And so if you went into petroleum engineering, that kind of field, you'd do some physical chemistry. And then biochemistry is, of course, life chemistry. And so you see this in medical careers, medical degrees, and just how your chemistry affects your organism, your life. Okay, so why study chemistry other than it's next on your schedule? The big one for me, and I hope and for you, is that it really can help you see and hopefully appreciate how complex God's creation is, the organization in God's creation, and just it really continues to point out His wisdom and just the cool way that He made some of these things. So even if you're not a fan of chemistry, just kind of keep your mind open to the fact that that it works and that God made it, and that's pretty stinking cool. Okay, also it can help you make decisions, what to eat, clothes to wear, whether it's cotton or something absorbent that lets you feel cooler if you're sweating, all that kind of stuff. That's all based on chemistry. It can help you make the decision on what kind of fertilizer to use on your yard when you have your own home. So it can help you make decisions about kind of everyday things. It's also something to consider as far as your career. Some of you may enjoy science, and I hope that you do, and so you may want to go into it. And chemistry is as always one of the big sciences as far as industry and uses and those kinds of things. So think about that one. Chemistry is a basic science. It's what everything else is based on, and so if you're going to start at the beginning, you really do have to start with chemistry. It also, just like math, unfortunately, can help you develop some critical thinking. Not only just the math problems, but it can also help you make observations, can help you really articulate if you understand and evaluate how it relates. And so it uses a lot of your brain. It can also be could be a political issue in some cases if the things that we are using, the vaccines, for instance, the one that they're trying to figure out for COVID right now, are the chemicals safe? Should we be using this? And so you need to be able to make an informed decision about how to keep yourself safe, kind of what you're going to do personally, but also how you might need to care for someone else or for parts of God's creation. Okay, so some uses. And if I were you, I would put some kind of little star next to this because this is a good list question on a test. what are some uses of chemistry? Chemistry is involved in the making of lots of materials. Plastics is probably the number one. Polymer science or polymer chemistry is one of the bigger fields. Different fabrics, like I already mentioned. It's also big in the energy industry, as you know, probably that some of you, especially you have parents that work for Phillips or ConocoPhillips. It is involved in the use of the fossil fuels that we are still trying to dig up, the making of batteries, nuclear power, which is becoming more prevalent for an energy source. Chemistry is also a big part of medicines, biotechnologies, so medications, of course, replacement organs, using like cloning and those kinds of things. And so the chemistry behind those is pretty complex. In the field of agriculture, they will genetically alter plants to make them disease resistant or to use less water, to make insecticides for the plants. And that is, again, chemically based. Environmentally, we want to be careful about conserving our resources, recycling, which involves some chemical changes. And then kind of a weird one that I threw in it, I believe it's still in your book, astronomy and space exploration. Things fall to the earth from the space around us all the time, and so figuring out what those are made of is also a field in chemistry. All right, so now the scientific method, which again, you guys have had, this will be your third year at least with me. This is another version of it, basically the same kind of steps. You see a problem that you need to solve, something that makes you ask a question. That's your starting point, and you develop your hypothesis, and this is your best guess for what is happening, and then you see if you're right. You test your hypothesis, you collect data, you do experiments, and you do the experiments a lot because you'll need to have a good set of data. And then finally you reach your conclusion, and this is once you've tested and retested, you've written up your results, and others have verified it, potentially could lead to a theory. Now, some other forms or some other ways to represent scientific material is through a law. And a law is a statement that summarizes the observations over time that describe a natural phenomena. There's no real explanation for it. Very often in chemistry, it is represented by a mathematical equation. And so, for example, Boyle's law, it's one of the gas laws. It says that as the container, the volume of the container for a gas increases, so as the container gets bigger, the pressure on the gas decreases. So if you take a certain amount of gas and put it into a bigger container, then the pressure is going to be smaller. And so it's just an explanation, it's just an observation. It doesn't explain why, though. And then you have, of course, a really simple mathematical equation that you can plug information into to determine how the volume changed or what the pressure becomes. So chemistry has quite a number of these scientific laws where they are just saying this is what happens. All right, so now measurements. This is where the math comes in. I know you're just on the edge of your seat. In your book, this is chapter 3, and for those of you who are in honors, you'll use that. You'll be a little more aware of that because of the questions that you'll do from here. So first things first, the difference between an observation and an interpretation. Observation, you use your 5 senses. You can see it, smell it, hear it, taste it, feel it, all those things. You're just simply looking or whatever. And then you have an interpretation. This is something that you infer from your observations. And so this is, I see this happening, so I believe this. Science should be based on observations, and it's not because unfortunately people are the ones doing the science, and so very often we interpret our observations and use our past experiences in those interpretations, or sometimes our biases, like what we kind of already have thought of. So this is for those of you who are writing stuff down as you go through this. You don't need to write this down. I just want you to read over it and then determine if the things below are observations or interpretations. Determine if they are something you can prove without a doubt through what is said or what you've read, or if there is some kind of interpretation that goes into it. Okay, so now the types of observations. Quantitative. Those are descriptions using numbers. These are the preferred types of observations as far as science goes, because you can't really argue with a number. And so, for example, if I say the book is 7 inches wide, you can't really argue with that. I mean, you can get your ruler out and you can try it, but if I measured accurately, then we're not gonna have a change. Qualitative is useful, but maybe less so, because it is based on the object's appearance, which means that someone could have some sort of bias, or you could just disagree. So, for example, if I say my notebook is red, you might say, no, I don't think so. It's crimson, or it's maroon, or whatever. And so there's a little bit of personal opinion that can go into the qualitative observations. So in that box, again, you don't need to write that down necessarily, but there are some examples of types of observations. So see if you can figure out if they're quantitative or qualitative. All right, so now scientific notation. This is going to come in handy as we get into more math in the time to come. And you've done scientific notation before, so I'm going to run through it pretty quick. But it is a method where you can express very large or very small numbers in a form that makes it easier to do the math. Now, really, that's not necessarily that true statement anymore, because we have calculators that can do scientific notation really easily. But if you're ever stranded on a desert island without your calculator and you need to do some big multiplying, here you go. So anyway, scientific notation, you have a number between 1 and 10, and it is multiplied by 10 raised to a certain power. And that power, I represent it by x, is an exponent, and that the number that you give to x is the number of places the decimal was moved to get your number between 1 and 10, which sounds confusing now that I'm saying it. But look at the examples here. You have large numbers, and they will always have these positive exponents. And so, for example, you have this number, which is really big. I should have figured out what it was before I started talking. So you have 386,400,000. And so if you want to put that into scientific notation, you need to realize the decimal is right back here behind the last zero, and then you will move it until you get it to between the 3 and the 8. So I usually just draw little loops, if I can do that with my pen. And so you draw little loops until you get to there. Oh, my first little loop didn't turn out so great. And then you just count the number of loops that you made. So you made 1, 2, 3, 4, 5, 6, 7, 8. And that number becomes your exponent. And then for small numbers, numbers that are less than 0, you do the same thing. You move your decimal until your number is between 1 and 10. So my decimal starts here, over here in this number. And so you will keep, sorry, my screen keeps doing dumb stuff. So you'll keep moving your decimal down. Sorry, don't really count my loops because they didn't turn out so great. But you will keep moving those down until you get to a number that is between 1 and 10. So 7.81 is in between those two numbers. and you would just count again. And so you moved it 8 places, and since it's less than 1, it's going to be a negative exponent. All right. I've got some practice on this next page, which again, you don't need to do, but I at least want to do the first one just to clarify. So if we have 8,362, I want my number between 1 and 10, good grief. And so I know that it's going to be 8.362. And then it's going to be times 10 because that's part of the format. And I have moved my decimal from here to here. And that required me to move it 1, 2, 3 places. So I would have 8.362 times 10 to the third. All right, so look at those other two and see if you can figure them out. All right, now calculations with scientific notation can be easy. Again, you're going to have a calculator, so you won't necessarily need to do these, but just as an example, if you're multiplying, you would multiply the numbers as usual without the times 10, and then you would simply add the exponents. And so that first example, you've got 2.4 times 10 to the 6th times 3.0 times 10 to the 7th. So if you multiply 2.4 times 3, you're going to get 7.2. And then you got to put your times 10 in there. And then you add the two exponents. So you would add 6 and 7. And so you would get 13. Now for division, you divide the numbers as usual, and then you subtract the exponents, the numerator minus the denominator. So you would do in that first example 4.8 times 10 to the 17th divided by 2.0 times 10 to the 11th. So 4.8 divided by 2 is 2.4. And then you'd say times 10, and then you would subtract 17, because that's the numerator, minus 11. And so you would get 17 minus 11 is 6. All right? Okay, so now the next step in measurement is determining or being accurate and precise. Accuracy is how close your value is to the accepted or to the correct answer. It's like getting 100 on a test. You are very accurate. Precision is how reproducible or how consistent your results are. And so that is consistently getting the same answer or the same result if you were doing an experiment. A percent error is basically like your grade, how close you are to being right. And so you would take your value minus the accepted value. Notice their absolute value, so it really doesn't matter which one you subtract, but drop a negative. And then you divide it by the accepted and times 100. This will give you a percent of some sort. And so your percent error you want to use to determine how good your job was when or how good a job you did. And it's basically like your grade. Okay, so now here is our trusty little bullseye, which I hope will help you see the difference between accuracy and precision. So if our goal is to make a bullseye, to be right in the middle there, and I am the person throwing the darts or shooting at this target, I'll tell you right now, I'm not very good. And so I'm trying to hit the bullseye, but I end up with my first shot here, my second shot over here, like probably not even hitting it, and then my third shot here. So I, with my first attempt, am not either one. I'm not accurate or precise. Okay, so then I practice and I come back, and somehow on the way out the door I got poked in one eye, and so I can't see as well, but I'm still going because I'm no quitter. But I can't, I don't aim as well. So now I start out and I hit my first shot here, not where I want it to be. I hit my second shot right around here. Not where I want it to be, but close to the first one. And then my third shot ends up here. Again, not in the bullseye, but pretty close together. So I'm still not accurate, but I am precise because my results are very consistent. Okay, so I go to the eye doctor. They help me get better. I go back for my third time, and I've got my 3 shots. And this time they go boom, boom, boom. And I basically am awesome. And so I finally have achieved accuracy and precision all together. Okay, so it's just kind of keep in mind kind of what you're doing as far as your results go. All right, here's another example. This is just some a little more of a science type example. And so it involves some measurements and determining, you know, how good you're doing. So look through that one. Again, you don't need to write this one down. Just kind of look through it and see what you think. Okay, now our next thing is significant figures. Significant figures cause some anxiety for some people, so just it's gonna be fine. First off, if we're talking about measurements, any measurement that you make using a piece of equipment that has markings like graduated cylinder, like you see on the page, or a ruler or yardstick or those kinds of things, those involve 2 parts. The answers are the what you write down. You have the digits that you can read with certainty, like you know that the mark is there, and then you have one estimated digit that gets people sometimes. So if we're looking at this graduated cylinder that's on the screen, the liquid in that little piece of the graduated cylinder you can clearly see is above the 35 milliliter mark. And then you can see that it is clearly above the 36. Each one of those little marks represents 1 milliliter. And so I know without a shadow of a doubt that I have 36 milliliters. But then you can see there's a little bit above the 36, and this is where the estimate comes in. So if you're going to estimate where that water level is, you can only use 1 digit. So to me, it looks like it's a little less than halfway there. So I'm going to say 36.4. Oops, that's my point. Where's my point? There it is. Okay. And so, so you have 1 estimated digit, and you may disagree on that estimation. My 4 might not be what you would put. You might put a 5 or a 6. The one thing you can't do is put 4, you can't put 36.47 or 36.59 or whatever it is. You can only put 1 estimated digit. All right. So just kind of be aware on the test that we take over this. You'll have to measure something and you'll have to do it correctly. Now just also be aware that the greater the number of divisions, so if it were, if I had more lines on there, then your instrument, your equipment would be considered more precise. Okay, so now the rules to determine significant figures. Significant figures are used to compare. If you are doing an experiment and someone else is doing that same experiment, you want to be able to easily compare them. And you do this by having the same number of significant figures. And so these are the rules. You're just going to need to be flexible. They seem to make people kind of irritated sometimes, and I understand that. So first rule, you always count non-zero integers. And so that means that if you had the number 127, you have 3 significant figures. Okay. Then second rule, zeros appearing between non-zero digits are significant. So if I had, let's see, 1042, I would have 4 significant figures. Okay, because the 0 counts because it is between, those are called captive zeros. Then the third, leading zeros do not count. This is one that seems to get people. Leading zeros do not count. They are simply placeholders. So if I had 0.000012, that number, I'm going to write it over here, has two significant figures. Sorry, I kind of ran out of space there. Just the 1 and the 2 count. The zeros don't do anything but keep the places. And then the fourth rule, trailing or rightmost zeros count if the number contains a decimal. And so you have two ways that this could play out, decimal or no decimal. And so if you had, I'm going to erase some of these others so we can have some space so I can write above them here. So if you had, for instance, if you had the number, let's see, 1,300. Like that, this number simply has two significant figures, okay, the 1 and the 3. If I had the number 1,320, and then I put a decimal right there, I put that dot at the end, I now have 4 significant figures. Oops, my decimal disappeared. That dot is telling whoever is looking at your numbers that you want to be able to compare 4 significant figures. All right, so I know it's kind of crazy. We don't really live in this world of data and comparing, but I just want you to know kind of what the rules are. And then the last one, exact number. If it's a number that's given or a number that is counted, then it doesn't affect the number of significant figures. It doesn't really even matter. Now, rounding, you guys know how to round. So basically, you might have to round to get to the correct number of significant figures. So, same rounding rules that you've learned your whole entire life. The number goes up by 1 if the number to the left of that last significant figure is 5 or more, you round up. If it is 4 or less, then you round down. So you can look at my little examples there in the green, and you guys will be fine on that one. All right, so now significant figures in calculations. If you are multiplying or dividing, your final answer needs to contain the same number of significant figures as the number with the lowest number of significant figures. So what that means is, if you look at this example, 4.56 times 1.4 equals 6.38. So that's, if you put it in the calculator, it's exactly what you'll get. But according to the significant figure rules, because I have this 1.4 here and it has 2 significant figures, my final answer should only have 2 significant figures. So that 6.38 is rounded to 6.4, so that I now have 2 significant figures here. They always have to match up. All right, addition and subtraction, it doesn't even matter about significant figures. It's the big thing to look at is decimal places, right? And so when you are dealing with adding or subtracting, you're going to give your final answer, around your final answer, to match the number with the fewest decimal places. So if I'm adding all these numbers up, I want to look at this 18.0. That 0.0 there's 1 decimal place, so your final answer should only have 1 decimal place. Okay, I'm not going to be super ridiculously picky on significant figures as we do more math. This unit I will be, because that's part of what I'm teaching you. So just don't get too anxious about it. Okay, so now metrics. In the scientific community, everything is in metrics, which makes sense. It's easier. We're just a little bit stubborn in America, and we don't want to do it. But in chemistry, we will. And so you have learned this before, and I've got the metric prefixes listed there. I do want you to make sure you have those written, and that I probably will have them up in the room or written somewhere, so you don't necessarily have to remember them. But if you remember that kilo is 1,000, then everything is just moving the decimal back one place. And so you've got kilo, hecto, deca, then your base, which is just the plain unit, and then deci, centi, milli. And if you remember those, you will be good to go. I always learned a sentence so I could remember the order. It was King Henry died by drinking chocolate milk. And if I knew that the K for king was 1000, then everything else I just took away a decimal place. So when you are converting between metric units and doing these metric conversions, it's really nice because you just are moving decimal places. You don't have to do any extra math. And so I've got this little metric conversion ladder picture. And so it basically tells you which way you're going to move the decimal. So if you're going, which way, depends on which way you're going. And so for example, that first problem I have up there, if I have 500 hectometers and I want to know how many millimeters that is, I am here, this spot up here, and I am moving down to this spot. So I'm moving my decimal to the right because I'm going down. So I'm going to move it 1, 2, 3, 4, 5 places. So I'm going to add 5 zeros onto the end of 500. So I, of course, didn't leave myself a big enough blank. So I'm going to have 500, and then I'm going to have 1, 2, 3, 4, 5 more zeros. And so I will go from 500 to, what is that, 50 million millimeters. So very easy, very straightforward. It's obviously preferred, but it is unfortunately not what we do most of the time because we use English units, and that often requires factor label. Oh, never mind. We'll do temperature conversions first. All right. So another conversion that I want you guys to know is to be able to convert from Celsius to Kelvin or Kelvin to Celsius. Kelvin is a temperature scale that is based on the movement of molecules. You will not go to Lowe's and find a Kelvin thermometer anywhere, but scientifically in some of the math that we do that involves temperature, it will have to be a temperature that is in Kelvin. The SI unit for temperature otherwise is Celsius, and so we will start with everything in Celsius, and it's a very easy conversion. You just add 273. And so there's a couple of examples. You can make sure you can work those. Get your calculator out and add or subtract. Okay, and now the factor label conversions. These are the ones that we have to do because we don't like the metric system. So we'll do a lot of these over the course of the year. I teach it very first thing so that you have time to work on it as we go throughout the year. Sometimes it doesn't click right away for people, and then when we come back to it more seriously, it's all good. So I know it's going to work for you. So I've got 3 steps for you. Remember I said that chemistry is kind of nice to teach because I can just give you steps to follow. So here's our first example. So you're going to start with this little this little grid that you're going to fill out, and you're going to have a given, and then you're going to know what you want it to be, and then you're going to know what you had started with. And you're going to fill in the number. You're always going to be given some information. You're going to fill in all the numbers, and then you multiply across the top, and you divide by what is on the bottom. So a couple of examples. You have 11 dimes, and you want to know how many nickels that is equal to. Chances are you can do that one in your head, which I hope you can, but I'm going to show you how to set it up. So here's our little grid, and my given is what I know already. I know that I have 11 dimes. And then I know over here that what I want to end up with is nickels. So there's some nickels. And then this unit's given up here, it's always going to match what you started with. It's always going to be what your given is. So here's dimes again. All right, so now I fill in these kind of blanks here and here with this information. Okay, so I know that for every 2 nickels, I have 1 dime. And then I multiply across the top, so I multiply 11 times 2, and I divide by the bottom, and so I divide by 1. So 22 divided by 1 is 22, which, like I said, you probably already knew, but I want you to, we'll kind of start with kind of the easy ones, and then we'll get to the tougher ones. So then on this next one, we have 23 inches. So there's my given, 23 inches. And we want centimeters. And here's our inches again, since they're always going to be the same. And I know that for every 2.54 centimeters, we have 1 inch. Oh, and I didn't work this out beforehand, so let me get my calculator here. So 23 times 2.54 equals 58.42. Now, if we're doing scientific significant figures, I only want it to have 2 significant figures because of the 23, so I would say 58 centimeters. Okay, so that's really nice and simple and very straightforward. There is, however, usually going to be many, many more steps, or not many, many, but more steps to these problems. So here's a multi-stepper for us to end on. So you use the same method. You still set up your grid. You still fill in the information as given. Just keep it going. Okay, so it's going to be long, long, look long. All right, so our example is if I have 4 squares, I want to know how many triangles that is equal to. So I'm going to start right here, and I've got 4 squares. And then if I look at my given information, I don't have anything that tells me the relationship between squares and triangles. The only comparison I have for squares are rectangles. So that's what I have to go to. So I'm going to go to rectangles, and then I have squares here, and then I fill in the information that I have. I've got 4 rectangles for every 5 squares. Okay, and if you want to, it might make it easier, just like math. If one unit is on top and the other is on bottom, they will cancel out. So now I'm trying to get from rectangles to triangles. Remember, I'm still, triangles is my goal. If I look at the information that I am given, I don't have anything that relates rectangles and triangles, but I do have rectangles and circles. And so I will go to circles. I've got my rectangles. And so now I have 2.7 and 3 rectangles. So now the rectangles cancel, and I'm stuck with circles. If I stopped right now, that's what my final answer would be, but I'm still trying to get to triangles. So my line wasn't quite long enough. So I have one more step, and I can get to my triangles because I have that last little bit of information. If I have 6 circles, they would be equal to 1.3 triangles. So, yay, I've got my triangles. Here's a circle, and I would then fill in my information, 1.3 triangles and 6 circles. All right, so now circles will cancel, and I am left with my triangles. Now, to do the math, you will do just like I said before and multiply straight across the top. 4 times 4, keep going, times 2.7 times 1.3 equals, you should get, if you punch this in, 56.16. Then, here's the next tricky part, dividing by the bottom. Do not divide, equal, divide, equal, divide, equal. Just hit divided by 5, divided by 3, divided by 6. And you are going to end up with a really tiny little number, and that tiny little number should round to 0.6. You're actually going to get 0.624, but if we do our significant figures, that's what you'll end up with. All right, so look that over. We're going to do some practice. Whether you are watching this because you are home for a time or you're watching this as a review, please feel free to contact me however you need to and ask me questions. We'll do some practice problems on these and make sure that everybody is on the same page. All right, thanks guys.